Hi everybody, welcome to another video in Calculus 2, section 6.4, volume by cells. So this is continuous from the previous section, volume by slicing. So there are two ways to find the volume. One way is just chop them up, and that's called slicing. And another way to do that is by shell. So, was the picture and I know, but if we draw the sketch, let's say we just want to find the area of something like this. One way to do that is we just slice that horizontally, and we find the cross section, and of course the width of the slice as well. So we have pretty much a small disk, and then we find the volume of one disk, and then the volumes of all the disk, add them up, we have the whole volume. So that's one way to do that. So on the big picture, that is either dish or washer. If there's the hollow region in the middle, that's a washer method. Now instead of doing that, what we do is we're not going to slice that. What we do is we do layer. So just make it layer like all onions, and for each layer we will have a cylinder, and the cylinder has a very small width to it, and we find the volume of each cylinder. By a cylinder I mean is a very thin shell. So that's the width of the shell, and we find the volumes of all of this, add them up, we will have the volume of the whole thing. So that is the volume by shell. So pretty much like we're trying to find the volume of this, we're going to take a shell and then find the volume of one shell, and then the volumes of all the shells, add them up, we have the volume of the whole thing. So now consider we'll slice, not slice, I should not use that word, we kind of take a layer out of it, and the layer of it will have the shape like this. So how do we find the volume of something like this? Notice for this one, what we have is the height of a shell, and then the radius, and what will be difficult to see because that's too small is the width. So the width of that, in this case they call the width delta x, or just call the width w. Yeah. Since we call this r, h, and the width of the shell w. Right, how do we do that? Now if it is a cylinder, so I'm going to make it like a cylinder like this, right? So if we're trying to find the volume of this, we can unfold that into a rectangular box. So we have originally the parameters here. I'll just use that camera. So think about this shell. The parameter, I should say the circumference of the cylinder, if you roll it out, it will be the width or the length of a rectangular box. So what we do here is we're going to turn that, and we just cut it and roll it out into a rectangular box like this. So in that case, what we have here is the length here is that. It's going to be the circumference of the circle, and then the circumference is 2 pi r. That is the circumference corresponding to that. And then we still have the height. The height h. And then the width w. So put all of that together, the volume of that rectangular box is going to be 2 pi r, the length, times the height, and times the width. So that is the volume of that shell. Now, we just need to find the volume of all the shells, and then add them up. We will have the volume of the whole thing. And ultimately, that's what the shell method is about. So, I'll go to the shell method. Shell method. Let f and g be continuous function with f of x greater than or equal to g of x on the a and b. So, of course, continuous function, that all of that's very typical. So we do know the limit from a to b, which is good. We don't have to worry about that. R be the region bounded by f of x and g of x, line by that. And then the volume of R revolving about the y-axis is this. Now, we worry about the x-axis and the y-axis later, but for now, for that formula, we can write the component as this. The 2 pi r, the x here is the radius. The difference of two functions is the height, and then the delta x is the width. So compared to the last problem, we have 2 pi r h and the width, and then the integral. So we find the volume. The integral is the summation of all those volumes. Right. So that's what we write in the note here. So in general, the shell, the volume by shell is equal to the limit from a to b, we know that, and then 2 pi. There will be three components, r, h, and then w. The w here can be either dx or dy. And similar to the this method, if we have dx, every r and h have to be in terms of x. If we have dy for w, it's going to be y. Everything have to be in terms of y. Right. Now, and finally, how do we determine dx and dy? Think about this. If we have the axis of rotation, slicing, we're going to slide the axis of rotation. So that will be like that. Shell is different. Instead of doing the slicing of the axis rotation, what we do is we're going to roll it like that, and we have one shell, and we have another shell just rolling around. So shell is wrapping around, and this washer is slicing it. So the way it works is depends on the axis of rotation. This one works completely opposite to what it is in the dish and washer. So earlier we said for the dish and washer method, if the axis rotation is horizontal, we use dx. This one we use completely opposite to that. So axis rotation is horizontal, we use dy. Axis rotation is vertical, we use dx. This is completely opposite to the dish and the washer method. We're going to write that note later. But okay, let's look at the first example. After a few examples, we develop the generalization of that. Right, so let R be the region bounded by the graph sine square, sine of x square, not sine square, sorry. So this. That is sine square, sine of x square. And the x-axis and the vertical line x equals square root of pi over 2. Oops, sorry, this will be this one. So we're talking about that, and when we rotate, it will generate a volume like this. Right. How do we find the volume by shell? So to find the volume by shell, first thing determine what is the axis of rotation. In this case, the y-axis. Right. So now on this one, I've just told you this is going to be dx. Later on, we'll determine why do we use dx and why do we use dy. Right. So vertical axis of rotation, we use dx, so it's going to be dx. So determine the axis of rotation. After that, we're going to take one layer of it, and the layer, so we just draw a line of the region that is parallel to the axis of rotation, parallel to the axis of rotation, and then we just rotate. We just rotate that around to generate a shell. Right. So how do we determine that? So first of all, this is going to be a shell method. So we just write V equal to 2 pi R H and then W, just in general. Now this one we know for sure, like I said, this first one we just use dx. Later on we will develop a more general sense of dx or dy, but it's going to be dx. So 2 pi R H and then dx. Now the x values go from 0 to square pi over 2. I mean to 0 to that, sorry. As soon as I write that, I know that it's the other way around. Going from 0 to square root of pi over 2. Right. Now we just need to determine an R and H. In this case, it will be kind of difficult because the way it is different than this method. On this method, we just have R squared and just determine R. That's simple. However, on this one, it's different. Alright. So notice that we have this, and we're rotating around the axis of rotation. So this is the shell. So what we draw there actually is going to be the height. So this gives us the height. And the height, of course, is going to be different of the two functions. The top, the one on the top, and the one at the bottom. So upper function minus the lower function. So the height is equal to the upper function sine x squared minus the lower function, the x-axis, which is y equal to 0. So that is the height. If you draw that cylinder, you see that it is indeed the height. Now, what will be the radius? So the radius is from the axis of rotation to wherever the point is. So if we talk about the radius, it is going to be this. From the axis of rotation to whatever this is. So what is the radius? Right. Of course, we see that the point there can be anywhere from 0 to square root of pi over 2. So actually, in this case, the radius is just going to be x. That is the x values. Yeah. So the radius here kind of different than the radius when we have in the disk or washer method. So just draw a line. That will be the height. Whatever the distance from that to the axis of rotation, that will be the radius. It might not be x. Sometimes maybe could be something else. Anyway, we put everything in here. 0 square root of pi over 2. 2 pi r is x. And then h sine of x squared, and then dx. Right. Now we'll just integrate this. This one we use substitution. And we'll let u equal to x squared, and then solve for dx. And then we substitute back into the problem to find it. Alright, so let u be x squared, because when we take the derivative of that, cancel with the x nicely. So we take the derivative. Move the dx over. And then divide by 2x. So we have two components like that. This one is the definite integral, so we have to find the limit as well. So the limit for x equal to 0 and x equal to pi over square root of pi over 2. So let's make a little table here. We have x, and then we have u equal to x squared. When x equal to 0, u equal to 0, 0 squared is still 0. And when x equal to square root of pi over 2, u will be the square of that, and the square of this one, square undo the square root, so just pi over 2. So we change the limits, and I'll substitute back into our problem. Two pi x still there, and then sine of x squared is going to be u, and dx is du over 2x. Now since we have u, the limit now is going to be from 0 and pi over 2. That will be limits for u. Right, simplify. Then x here cancel with that x, and there's a 2, cancel with the 2. So we end up with 0 to pi over 2. Actually, we can take the pi outside as well, but just pi sine of u du. Now integral of that, integral of sine is negative cosine. Both negative pi cosine of u. Right. And then we put pi over 2 and put 0 into it first. Put the pi over 2 into it. And subtract where we put 0 into it. Alright, cosine pi over 2 cancel out. Cosine pi over 2 is 0. And cosine of 0 is 1. And negative, so that's just a pi. Because we have a calculator here, why don't we just check? Make sure it is in the radian mode. Alright, it's good. Math number 9, going from 0 to square root pi over 2. Here we have 2. Just going to put this in. Pi. Actually, we should leave the pi outside. Right? And then x sine of x squared. Notice that I leave the pi outside. And the answer of this is 1. And then we put the pi back in. So it's pi. Because if I put the pi in here, a second insert a pi into it, when we look at this answer, we know that is pi. But I said if we use a calculator, leave the pi outside, so we have a nice fraction usually, then we put the pi back in. In that case, we have the exact answer, because if we have pi over 7, then we won't be able to tell it. So leave the pi outside first, and then at the answer at the end, just put the pi back in. Right, so that's what we have for that problem. Again, whatever the axis of rotation is, draw a line parallel to it. That will be the height. And the radius will be from the axis of rotation to that point. And that point can vary anywhere here. So that's why we use x for it. Right. Now, let R be the region in the first quadrant. So it's in the first quadrant bounded by square root of x minus 2 and the line y equal to 2. Right. So first, square root of x minus 2, it is the standard square root, move 2 units to the right. Right. Now, next, find the volume of course, and then the line y equal to 2. And this is in the first quadrant. So we're talking about this region R is this one here. Now, most importantly, axis of rotation is the x-axis. So we rotate, and we have a shaft like this. It is a cylinder, but take out a paraboloid. Right. Now notice that this one is different. On the earlier we have the vertical axis of rotation, we use dx. This one, the horizontal axis of rotation, we use dy. So let's just write a little note before we go on further. So if the axis of rotation is vertical, something like the y-axis, sorry, couldn't see that, then we're going to use the width is equal to dx. Now if the axis of rotation is horizontal, in this case, is horizontal, W is going to be dy. So remember, in general, let's say if we have the vertical axis of rotation. Then the distance washer method, we're going to slice it. And of course, each one of the slice is going to be dy, which is parallel to it. Now, if the axis rotation is vertical, in the shell method, we do not slice it. What we do is we graph around, so one layer, and then graph another layer on the outside, and then there will be another layer outside. They're just graphing around it. So in each layer is going to be horizontal component. So that's going to be the x instead. So either we use that or we say whatever the axis is. If it is the shell, it will be okay. Whatever the axis is, I'm just going to say that axis, the shell, and this method we determine like this. Whatever the axis is, if we're going to slice it parallel to it, it's going to be this method, and perpendicular to it, it's going to be the shell method. Right. So we do a lot of examples between the two. So for now, I just do this one first. So in general, we know that the volume by shell is integral 2 pi r h and w. Since the axis rotation is x-axis horizontal, this we use dy. And what is the limit for y here? Easy to see, from 0 to 2. Right. Now determine the r and the h. The h is where we just draw a line parallel to the axis of rotation. So I'm just going to draw a line here. And that will be the h. Now notice that this is in terms of y, so we have to turn everything in terms of y. So first of all, y equal to square root of x minus 2. If we turn that into y equals square root of x minus 2, square both sides, y square equal to x minus 2, and plus 2 over, so x equal to y square plus 2. So that is the curve here. In terms of y will be y square plus 2. And then that. Right, first, so the height is going to be that, which is the difference from the function on the right minus the function on the left. So the function on the right in terms of y is y squared plus 2. So it has to be in terms of y. And then we subtract the function on the left, which is the y-axis, or x equal to 0. Right, so that's going to be y squared plus 2. That's the height. And then r. Right. I said usually this is the big tricky when we determine the r. So r is the distance from the axis of rotation to whatever the line we have here. So we can talk about this is r. or we can say this is R. Either way, if we have a point here, x and y coordinate, think about that point has x and y coordinate. That distance is going to be the y coordinate, right? Right. By the way, R is not always x or y. This could be something else. We'll talk about that in the next few examples. But for now, putting these components in 2 pi r is y, h y squared plus 2 dy. Now the constant of 2 pi, we can take it outside of the integral. And I'm just going to put that in the calculator at the end, multiply by 2 pi. I should have the answer. Like I said, the focus on this section is not to integrate, but to get the values. I mean, to set up the integral. Right, we need y, so alpha 1, alpha 1 plus 2. Close. And the variable is y. So do that, we should have 8. So that gives us 16 pi. Right. So on the shell method, determine what is the axis of rotation. In that case, we will know that if it is dx or dy. After that, we draw a line parallel to the axis rotation. That gives us the height. And the radius is the distance from the axis rotation to the point. Right now we go to a summary here. This is the summary for addition washer method and then the shell method. So let's say we have trying to find the volume of this one rotating about the axis rotation is 6 here. That is, let's say 6. Here we have 5, 1, and the function here we don't know. But what we know here is the function here is either y equal to f of x or x equal to g of y. So it could be either in terms of x or in terms of y. And so we have that function. And then, let's say if we do the dish and the wash or washer method. Dish and washer method, the axis rotation is axis of rotation. There must be an abbreviation for that. Axis rotation is y equal to 6. In this case, it is horizontal. And then the axis rotation. This washer is the slicing, so we're going to slide the axis rotation. Therefore, each small increment is going to be dx. So this is the dx problem using dx. Right? So for this washer method, it is going to be v equal to pi big R square minus little r square. In this case, it is going to be dx. And x go from 0 to 2 for this region. Yeah, 2 for x. Now what is big radius? Right, the radius is always from the axis of rotation to the edge. This one we have to the outer edge. For the big R, and then the little R to the inner edge. So in this case, the volume is equal to 0 to 2 pi. Now, the big R is going to be 6, the function above, minus the function that is below. Upper function minus lower function. Upper function is 6. Lower function is f of x, because that in terms of x. And then little r, above is 6, below is 5. So we just that, right? 6 and then 5, so it's just 1. Of course, we can integrate this, but we don't have the function, so we're just going to leave it at that. Next, if we use the shell method for this one, axis of rotation is still here. So let, for now, just say it AOX, axis of rotation. Little o, axis of rotation. So now we have AOX, a rotation I can't even spell right. So axis of rotation. That better. So that's how we abbreviate it for now. Axis of rotation is y equal to 6, which is horizontal. So what we do is, we do not slice it, we wrap around. And when we wrap around, the thickness of the paper here is going to be the width. So of course the thickness of that is going to stack up vertically, so it's going to be dy. So you see, for this and the washer method and the shell method, they're going to opposite way. One is dx, the other one is dy. Right. So the volume by shell, 2 pi r h, and the w here is dy. Y go from 1 to 5. Right. Now to determine the r and the h, this is the axis of rotation. To find the h, we'll just draw a line parallel to it. And then when we draw the line parallel to it, let's say one of those endpoints, x and y coordinates. Let's do that. So I have the h. So h is going to be the function on the right minus the function on the left. So the height is equal to function on the right. In terms of y, will be g of y. Subtract the function on the left, which is 0, which is g of y. So the height, g of y, substitute into here. Just draw a line parallel to it, that will be the height. And on the line to it, just put a point there, either anywhere on the height. Let that coordinate be x and y. Right. Now, determine the radius. The radius is from the axis of rotation to that point. So this is the radius. So how do we determine the radius? Now notice that this point is coordinate of that point is x and y. So meaning that this is going to be y, right? And this is going to be x. Now if this is y, the whole thing is 6 minus y. It's going to be r. So r is going to be equal to 6. The whole distance here, take out that distance y, and that is r. So we have first r is 6 minus y, and then h is g of y dy. Right. Now this one, we have the same region, still same function, y equal to f of x, or x equal to g of y. Axis rotation, this time it is x equal to 3. Axis of rotation is x equal to 3, which is vertical. In addition, what's the method? We're going to slide the axis of rotation. So if we go by increment like that, of course this is going to be dy. So this is what's the method? We're going to use dy. And so that this is what's the method, and we use dy. Limit for y though, 1 to 5 for y. Now what are the radii? So radii from the axis of rotation to the outer edge. From here to the outer edge. The function on the right is 3. The function on the left is 0. So that is 3. That is the big R. Little r. From the axis of rotation to the inner edge. The function on the right is 3. The function on the left is the function itself, but have to be in terms of y. So it will be g of y. So if this is y, everything here have to be in terms of y. So we use g of y, and we substitute in here, and that's what the integral will be. Of course, this and the Watson method, remember there's only 1 pi, not 2 pi. Sorry. Just a pi. R square will be 3 square. Minus little r square, 3 minus g of y square. Right. Cannot integrate this because we don't have a function. Right, so that's. Next, still axis of rotation is x equal to 3, which is vertical. So for the shell method, we do not cutting the axis of rotation. we wrap around it. So if we wrap around it, the radii will increase horizontally. So this is going to be dx. And the shell method, 2 pi rh, and then the width is dx. X goes from 0 to 2. Right, what is r? Now to determine r, we're going to draw the line parallel to the axis of rotation. That gives us the h. And then to determine the radii or the radius, just pick any point randomly on the line we just drew. I will choose this point, kind of random point, right? That point has the coordinate of x and y to be determined later. Right, just pick a point there, x and y coordinates. Right, now, the radius, the height, sorry. The height is this, a function above minus the function below. The upper function is 5. The lower function is whatever the function is in terms of x, so f of x. So that is the height. Now the radius. The radius is from the axis of rotation to that point. Now we call this point x and y coordinate. So this is going to be x and that one is going to be y, right? So x is the distance from that point to the y-axis, and since the whole thing is 3, take out x, so r is going to be the whole thing 3 minus x, so r is 3 minus x, and we subtract them. So finally put in here, so integral will be 0 to 2 pi, the radius r 3 minus x, and the height 5 minus f of x dx. Right. So just write a little note here before we go any further. So if the axis of rotation is vertical, example of that is vertical is like the y-axis. If that is the case, the dishwasher method is going to stack in vertical as well. So this in washer we using dx, dy will be the same. By the same, I mean the same component or same vertical. So if it is vertical, dy, the increment is also vertical. And then if we use the shell method, we're going to use dx. So vertical axis of rotation, parallel to it is the dish and washer method, perpendicular to it is the shell method. Likewise, if we have the axis of rotation is horizontal, like the x-axis, this in Western method is also horizontal. And the shell is opposite to that. Right. So that's a comparison between the two. Now we go to a bunch of examples and using both this and Western method and then shell method. But so keep that in mind. Right, now we have the first example. Right. Let R be the region bounded by. So I use the script R here instead of just the R for the radius. So just want to be distinguished the two. Right, y equal to x cubed, y equal to 8, and x equal to 0, and then rotating about the x-axis. Right, y equal to x cubed. That's easy. So look like that. Y equal to 8. And x equal to 0, which is the y-axis. And of course, we're talking about that. This one here. Now, this one, first we use the dishwasher method. Right, axis of rotation is the x-axis. Right, dishwasher method. Now, first, axis of rotation is the x-axis, which is horizontal. So horizontal, the dishwasher, the increment is also horizontal, meaning that we're going to use dx. So that's the first thing we determine is that the x or dy, because we need to base all the function in terms of x or y. In this case dx. So we know for sure pi r square minus little r square, and that will be dx. Also, when we know x, we know the limit from 0 to 2 for that region R. Now, big radius, little radius. So big radius is from the axis of rotation here to the outer edge. The function above is 8, the function below is 0. So R is 8, big R is 8. And the little radius is from the axis of rotation to the inner edge. So pretty much the top function is x cubed. Remember, we use x. Subtract 0, which is x cubed. So we're going to have 0 to 2 pi big R 8 square minus little r x cubed square dx. I can take out the radius r, which is constant. a squared 64, x cubed squared x to the 6. I just get the answer here. Integral math number 9, that go from 0 to 2. 64 minus x cubed, I mean x to the 6, sorry, and then dx. Right, I put this in fraction. Right, 768 over 7, and let's stick a pi to it. So the answer is 768 over 7 times pi. Right, so that is the volume used in the dish or the washer method. Next, for the shell method, axis of rotation is the x-axis, which is horizontal. Now if it is horizontal, the width has to be perpendicular to it, so it's going to be vertical. The vertical increment is going to be dy. So the shell method is going to be dy, and the volume is equal to 2 pi r h, and going to be dy. Right. Get back to that, but first let's draw y equal to x cubed y equal to 8 and x equal to 0. We're still rotating about the x-axis. Right, now since this is dy, the limit for y is 0 to 8. Now just need to determine the component of r in h. So for that, axis of rotation is this. Just draw a line parallel to it. So it will be here. That will be the height. And I will pick a point on it, on this line. I choose this point. The coordinates x and y. So actually this is going to be x and this is going to be y. It's not at 2, it's a little off there. So that is y. We don't need x here, right? So because we use dy, so if this is the point x and y coordinate, the y component, the y coordinate is going to be that. We don't even need x. Throw that away. So that is y. Right, now r is determined later. Sorry, let's go by h first. H is this much. It's function on the right minus the function on the left, but has to be in terms of y. Right. So equivalently, y equal to x cubed. We can say x equal to y cubed. Cube root of y. Sorry. Take the cube root on both sides. We have x equal to cube root of y. So that is the function on the right minus the function on the left, which is 0. Or just y cubed, I mean cube root of y. And then r is from the axis rotation to that point. So that coincidentally, that is y. So yeah, we have r by h. Put in the integral. R is y and h is cube root of y. And this is dy. 2 pi is a constant, so take it outside. And we have y times cube root of y. I'm just going to use a calculator here. Math number 9. That goes from 0 to 8. Y and cube root, let's say times cube root will be math, option number 4 of y dy, and that is something. Convert to fraction. Shoot. You cannot really get a fraction out of it, but here we expect the answer to be 768 divided by 7. So without the pi, without the 2, sorry. So let's say 768 divided by 2. So we have 384 instead. So how about 384 divided by 7? That should be this. Yep, you see. So that we'll have 384 over 7. We should do this by hand. But when you multiply by 2, it gives us 768.7 pi. In fact, if we just do this, and we're going to put 2 pi to it, that is our answer. And if we compare to this, 768 divided by 7 times pi, of course, it should be the same thing. So, because we calculate the same volume, just different way. Right, now, another example. Also dishwasher and then shell, using both. Right. Let R be the region bounded y equal to x squared, so the parabola y equal to 2 and the y-axis. Y equal to x squared y equal to 2 and the y-axis. So we're talking about this region here, and the axis rotation is x equal to 3. That's interesting. Right, so this is washer. First, axis of rotation is x equal to 3, and this is y equal to 3. Sorry about that. This is axis rotation, x equal to 3. Right. At least we didn't go any further. So x equal to 3. So we rotate about this one, not that one. Sorry about that. Right. So x equal to 3, so the axis of rotation is vertical. So if we use the dish and the washer method, this is going to be also vertical. So we're going to have dy for dish and washer method. So it will be v equal to something to something pi r square minus little r square dy, where y in this example go from 0 to 2. Right, now determine the radii. The big radius, we're talking about this here. The big radius is from the axis of rotation to the outer edge. So that is the big radius. Function on the right 3, function on the left 0. And the little r from the axis rotation to the inner edge. That is little r. Now this has to be in terms of y, so I will convert this function to y equal to square root of x. Could be plus or minus, but we're talking about positive in the first quadrant, so y equal to square root of x. And the distance will be from the function on the right, which is 3, subtract the function on the left, square root of x. Shoot, sorry. As soon as I wrote that down, I know that's wrong. This has to be dy, right? So everything have to be in terms of y. So y equal to x squared is equivalent to x equal to square root of y. Sorry, that was my mistake. Of course, when we put it back in here and we see there's x in there, we know there's something wrong. Bottom line is v equal to 0 to 2 pi big radius square minus little radius square right. Just set it up, and that's what we have. Of course, we can take the pi outside too. Right, so big radius from the axis of rotation, to the outer edge. Small radius from axis of rotation to the inner edge, whatever smaller. Right, shell method. Right, first I will draw this again. Y equal to x squared, or of course equivalently x equal to square root of y. So actually we don't know if it is x or y, so usually if we have a function, just do both. X equals something y and y equals something x. Y equal to 2. And the y-axis, x equal to 0. Still the same region there. The axis of rotation, x equal to 3. So axis of rotation is vertical. That means in the same method, it has to be something horizontal, which is dx. So So opposite those two always, one is dx, one is dy. And the distance vector will be parallel to the axis of rotation. The other one is perpendicular to it. So shell method, v equal to integral 2 pi rh, and then the width is dx, and x in this problem, it will go from 0 to y equal to x squared, or x equal to y squared. I mean x equal to square root of y, x equal to square root of y, and y is 2. So this is square root of 2. And now we have r and h. To determine r, we draw the line parallel to it. I mean to determine h, that is h. And then we just pick a point randomly on this line. Because I can just put this one, why not? And then x and y coordinate. Now since we're only interested in the x coordinates, right? Because this is the x. So actually this is the x component of it. Alright, now r, to determine r from the axis of, r and then h. Right. H is that much. So that distance is going to be the upper function minus the lower function above minus the function below for the h. So above is y equal to 2, the bottom is x squared, so 2 minus x squared for h. And then the radius from the axis of rotation, which is here, to that point. So that is r. Notice earlier we called this point coordinate, this coordinate is x and y. Since this is dx, we only focus on x, which is this component here. Now since the whole thing is 3, take out x, we have r. So r here is equal to 3 minus that portion. 3 is the whole thing minus x, give us r. And we're going to put that into the integral. 0 to square root of 2 pi r is 3 minus x, and h 2 minus x squared, and dx. So the first thing we determine is x and y, dx or dy, and then the function will follow. We use either x or y. Where we draw the point here, we just also need to know what is the x coordinate. We don't need y anymore. So that is x. Right. We have 2 more examples here. Like I said, these videos are recorded, so if you need to pause the video, of course you can always do that. Right. Next we have R be the region bounded by 2 to the x power, well, y equal to 4 and x equal to 1, right? So what is the graph of y equal to 2 to the x power look like? So when x equal to 0, 2 to the 0 power is 1. When x equal to 2, x equal to 1, 2 to the first power is 1. x equal to 2, 2 squared is 4. So I have exponential function and then y equal to 4. And then x equal to 1. Vertical line. And we talk about this region here. And this one, the axis of rotation is x equal to 1. So about axis of rotation of x equal to 1. So this is also the axis of rotation. Axis of rotation x equal to 1. Right. Now let's just draw the other two. Again, we're going to use both, so I'm just going to divide the pages in 2. Right, x equal to 1 and y equal to 4. Right. Now, x equal to 1, y equal to 4, we cannot really switch to x and y. But y equal to 2 to the x, let's write that as x equal to something y too. So because we don't know if we use dx or dy, so let's just write that. So y equal to 2 to the x. How do we write that? As x equal to. So let's see. Y equal to 2 to the x. Just trying to write right here. Y equal to 2 to the x. If we want to solve for the exponent, we check ln on both sides. The exponent will come outside. And then we divide by ln of 2. So it's just that. Now we have the formula of chain of bases. Log base b of a is equal to ln of b over ln of a. Yeah, so this is just ln. Just put that badly. So this is log base 2 of y. So equivalent to y equal to 2 to the x is x equal to log base 2 of y. So we don't know which one do we use yet. But if we use x, we're going to use 2 to the x. If we want to use y, it's going to be log base 2 of y. So be either way. Right, now let's use addition washer on this side and the shell method on the other side. Right, dishwasher. Right, now axis of rotation is x equal to 1, which is vertical. So the increment dx or dy have to be vertical as well. So dishwasher will be aligning with the axis of rotation. So this is going to be dy. And the shell method is going to be dx. So one should be dx, the other one is dy. Right. What is the big radius? The big radius from the axis of rotation to the outer edge. So here to the outer edge, that is r. The little radius, well, there's none, because the region and the axis of rotation, the axis of rotation is part of the region r. Therefore, there's no gap between them, so there's no inner radius. R equal to 0, because from the axis of rotation to the inner edge, that distance is 0. So if it is 0, it's called the this method. And so we just have v equal to pi r squared. That's just the this method. We use dy. And y goes from 2 to 4. Right. Now what is the big radius? From the axis rotation to the outer edge or to the edge. And so that is all. The function on the right is this, but has to be in terms of y. So we're going to use this one. Function on the right minus the function on the left, which is 1. So r is equal to log base 2 of y minus 1. And then we square that and dy. Now the shell method, we're going to use dx, and the shell method it's just one formula. There's not two like this in the washer. At least we're going to be 2 pi r h. Now we know it's going to be dx. And x in this case going from 1 to 2. Right. How do we determine the height and the radius? So the axis of rotation is like that. So we're going to write a line parallel to it and call that h. At the same time, just pick a point on that line and we'll have the x and y coordinates. But in this case, we focus on the x coordinates. The x coordinate, which is the horizontal distance. So that is the x coordinate, right? From that point. Right. First, the h, the height. The height here, the function above minus the function below, 4 minus log base 2 of, okay, going to be 4 minus, we're going to use x here, so have to use the function that have x in it. So 4 minus 2 to the x. Function above minus the function below. And then how to determine the radius. The radius is from the axis of rotation to that point. So we're talking about the radius is extremely small. I cannot zoom in the camera anymore, so hold that very close here. So we're talking about the radius be from that point to this point, very small. Yeah, very small distance from axis of rotation to the point. So that is all. Now, the whole thing is x. Take away this distance is 1. So we have x minus 1 is going to be r. And then we put it back into the formula. Here we have integral from 1 to 2 up to pi. The radius x minus 1. The whole thing is x. Take away 1, give us r. And then h is 4 minus 2 to the x. And this problem is dx. And if we evaluate both integral, we should be able to get the same thing. However, we won't be able to do that because this will do that in section 8.2, iteration by parts. For now, nope, can't do that yet. This one we can, but I said, important thing here is how to set this up. Right, next. Let R be the region bounded in the first quadrant. So we do know that this is in the first quadrant. Y equal to sine x and y equal to 2 over pi x. Right? That's a little bit odd. Y equal to sine x. So sine of 0 is 0. Sine of pi over 2 is 1. And sine pi is back to 0. So we're talking about that part of the sine in the first quadrant. And then also we have y equal to 2 over pi x. So when x equal to 0, we have 0. When x equal to pi over 2, 2 over pi times pi over 2, they are reciprocal. So it's going to be 1. So indeed we talk about that one. And here we have y equal to sine x. All right. Now if we don't know if we use dx or dy, why don't we just use both? If y equal to 2 over pi and x, so for x will be equal to pi over 2y. We don't know which one we use yet, but we're just going to do both. Y equal to sine x, and in that ninth quadrant, x equal to sine inverse of y. Right, so we're just going to write both. Don't know which one we use yet. Right, this and washer method. Let's say over here we use this and washer. And over here we use shell. Axis of rotation, y equal to 2. Rotating about y equal to 2. Right. First thing first, do we use dx or do we use dy for the this and washer method? So axis of rotation is y equal to 2, and that is a horizontal axis. Now if it is horizontal, then the x or dy have to also be whatever it is has to be horizontal as well. and the dx is the horizontal. So we use dx. Now, talk about this. Very small region here. Well, it's going to be tough when we do the shell method because that's too small. Anyway, worry about that later. Is this a dish or a washer method? All right. The axis rotation is way over there, and the region is here. And there's the gap in between. So that is a washer method. And we use dx here. And x goes from 0 to pi over 2. Right, what is the big radius? The big radius is from the axis rotation to the outer edge. The outer edge is the line. And so the function above is 2 minus the function below, which is the line. And by the way, since we use x, we're going to keep the function in terms of x. So it will be 2 minus that. That is the big radius. The little radius is from the axis of rotation to the inner edge, which is this function. And since we use x, we're going to use that. So r is going to be upper function minus lower function. That is little r. Substitute in there, we will have 0 to 2 pi big radius minus little radius and so just like that. Now for the shell method, if this is the x, the other one is going to be dy. Axis of rotation is y equal to 2, which is horizontal. So the increment should be something vertical, perpendicular to that. So we're going to use dy. And if we use dy, it will be 2 pi h and dy. The limit for y going from 0 to 1. Just need to determine r and h. In this case, kind of small and difficult to determine that. So axis of rotation is that. We're going to draw a line parallel to it. So very small here. That is h. Right. So on the region parallel to the axis of rotation, that is h. And we're going to pick a point there. That point has the x and y coordinate. But since we have dy, we just worry about the y coordinate. So that is y and that is h. So h is that, which is the difference between the function on the right, the line, the function on the left, the curve, in terms of y though. So we have to use the function in terms of y. The function on the right, the line minus the curve, the line minus the curve. that is h, the height, parallel to the axis of rotation. Now r, to determine r, from the axis of rotation here to the point, so the whole thing is from here to there is 2, right? Take away y, give us r. So r equal to 2, the whole thing, minus y. So we have that. And then we put it back into here. We have the integral. Two pi r 2 minus y h pi over 2 y minus sine inverse y dy. Right. So the dish or washer method compared to the shell method completely different. If one using dx, the other one using dy. And we didn't go to any complicated example where the function changing. Like if we have something like this, rotating about some axis, that would be difficult because we have something different between the function and not consistent. Luckily, we not go to any that complicated. Usually the r, big R, the radius is from the axis of rotation out. If the dish and washer, we have the inner radius and outer radius. The big radius, the little radius. For a shell, we only have one. From the axis of rotation to the point. That point though, either x coordinate or y coordinate. Since this one is dy, we worry about y. This one is dx, so we worry about x only. Ignore the other one. And then from the axis of rotation to that point, we just have to draw it and be able to see if it is whatever it is for the axis of rotation for the little r. And then bottom line is, in terms of the axis of rotation, the dish and the washer method, the first thing we need to determine is whether we use dx or whether we use dy, and everything else will follow after that. And usually when we draw the function, just do both x and y, and then depends. If we use dx, we use the function of x. If we have dy, we use a function of y. Right. So this need a lot of practice to get used to the dish and washer method, especially when the axis of rotation is not the traditional x-axis and y-axis. But I cover all the example that I need to. So I'm going to end the video here, and as always, thank you for watching.